JPL, and she is working in the MSL, Mars Science Lab mission. And she's going to tell us a little bit about herself and about the mission itself. Okay. So if you want to ask questions, you can put them in the chat so that you remember, or there will be some time at the end for questions. Okay, Alicia, it's to you.
Good morning. And so I understand this is a physics class, right? I remember taking physics in high school, but at that point in time, I actually was more interested in going into medicine. So I thought I would go off and be an anesthesiologist or maybe a doctor in medicine until I took high school physics. And my brother convinced me to take high school physics, and I loved it. I decided that that's more the direction I wanted to do. So when I started college, I switched from medicine to engineering on my first day, kind of things, because I wanted more math in my life than medicine was going to let me do. Although I think I could have had more math in there than I thought there was, like with MRIs and that kind of scenario. So there's some areas where I could have maybe done more math, but maybe not the math I'm doing now. So I then ended up working as an engineer and came to NASA as my second job out of college. So let me share and we can get started here. So yes, can you all see that? Yes, yeah, all right. So this talk is from a couple of years ago, so there's some things that have changed since this point, mostly that we've done more in the last couple of years than I have in this talk. Okay, so let me get here and get it moving. There we go. So first I want to let you know that it's not a small mission. I am only the messenger here. I'm talking about work that's been done by about 200 engineers and managers, of which I also am one of those, and about 500 scientists all over the world participate in this mission. So it's been going on for quite some time. We landed in 2012. And when you take a trip or you take on any kind of endeavor that you want to do, like you want to go to Costa Rica, isn't that what I heard earlier? Costa Rica, how do you decide you're going to go there? Well, why do you want to go? Are you going to go there to take a class, or are you going to go there to look around at things or be a tourist? So in the same way, the mission has a goal. It's like, why do you want to go to Mars? What do you want to find out? Well, we are looking for the potential habitat for life, and not just life now, but life perhaps past or present, or maybe even future, but more likely past or present. So that's what our sort of mandate was. If you go to Mars, what would you like to investigate? And that was what we're looking for. And so one question is then, where do you go? Because the entire Mars, this is a map of all of Mars in true color. So if you were to look at Mars and map it out, it would look like this, sort of like our global map. Where would you want to go? Well, you shouldn't go somewhere someone else has already been, which is what all these missions are. We had a lander up here. This was our first rover, Opportunity. You may have heard of Opportunity and Spirit rovers that had been there. So we chose a spot. And so why was that spot so interesting? Well, that's really because if you look at it instead of true color, but in a topography map on how high up things are or not, each of these colors is a different altitude. So this is like one of the largest mountains in the whole solar system. And it gets down to even below that sort of equivalent of what we would call sea level, since there's no seas. We don't quite have that on Mars. And so they looked at this and said, these different layers are what we're more interested in. And they chose Gale Crater because it's on the edge of seeing that you get all these different heights and layers all in one spot. So they're like, that's where we want to go investigate and see the layers, which are the history of deposits of dirt and how they've turned into rock throughout time. So it's sort of looking down in time and not having to dig down deep to get there. So how big is that crater? This is how big that crater is relative to where you are. So in the middle of this is Guatemala City, and that crater covers a huge area all the way over to Lake Atitlan down to the beach. So if you've ever gone to the beach, that's how long it took to get to the edge of the crater. Or if you've gone to Lake Atitlan, and I've been to both of these places, it's quite a drive, right? And we landed sort of in this area up here. So this is what the crater would look like if Guatemala City was in the center. This was our landing ellipse. So this 20 by 7 kilometers, and that little star is actually where we landed in it. So this 20 by 7 kilometer little ellipse had to be in the flat zone so we could land safely, but we really wanted to get to some of these layers of rocks so we could start investigating them. And if you turn it like a GPS, this is what the path looked like. So we landed up here in the north and we wanted to go into and up the edge of this mountain called Mount Sharp, which is taller than any of the volcanoes in Guatemala. It is 5.5 kilometers high. So this is a pretty tall mountain, but we didn't want to get to the top. We want to get to these layers along the side. So we got to get off the smooth spot, get up these layers. How are you going to do that? Well, you do that by taking your geologist with you. So we're acting as if we're a geologist, and we took a lot of the same geological tools. You want to check on the weather, you need to take a lot of pictures and see. You want to have stuff on the end of the arm here so you can bring your tool pack. We'll talk about that in just a second. But also things that will analyze the rocks a little bit on the surface. And these two down here, the SAM and the Kimin instrument, do what I call crime scene investigations on Mars. Have any of you seen CSI? Have you heard of that TV show? Some of them, maybe, yes? Well, that's what these two, so we not only took the geologist, we took the geologist laboratory with us, and that's what these two instruments do. So we can take a little bit of this soil in the form of rock dust or sand or soil that we scoop, put it into these two instruments from the top, and they will analyze it and tell you exactly what it's made of, and Kimin will tell you what form it's in. So Sam will say, it's pure carbon, and Kimin will say, it's graphite or it's diamonds. Now, not that we found pure carbon, but that's the kind of things it will tell you. And along with that, you have to be able to get around and actually maintain it. So the car equivalent has, the rover has many different tools at the end. So we have a drill to drill holes in rocks. We have a brush to brush off the dust so we can look at them more carefully, and a scoop, as well as sort of a sieving system that will take that dust and get only the particular particle size to put into this laboratory that we brought with us. Of course, we have 17 cameras with us. There's some for driving, and there's some that are just for scientific investigation. And this one, KimCam, actually has a laser that will ablate the rock. It will melt the rock about 1 millimeter, but it will melt the rock, which then creates a poof of plasma. And then the telescope, basically, telescopic camera, will take an image of that and do a spectra and tell you what that's made of from 10 meters away. So we can tell from 10 meters away some of what it's made of, decide we like it, drill a hole in it, and analyze it further. So this thing is really big as rovers go. It's kind of small as cars go. So if you're used to cars, it's more like a Mini Cooper, but wider. So this white part here, so this is the actual rover in the clean room where we put it together, that is currently on Mars. So it's wrapped up a little bit. So the drill bits in the front are all covered with a Mylar anti-static covering. But these are the 4 cameras, the HAZ cams, we call them, the hazard cameras in the front. This set of cameras is looking over its shoulder, and these wheels, so this white part is about the size of a twin bed. If you've got a single bed at your house, it's like the size of that, but it's about a foot or so, half a meter thick, and that hits me right about my waist, and this camera at the top is above my head. So if you sit up, put your hand all the way up, that's about where the camera is. And then the wheels are really far apart so that we can be very stable with this nearly 2,000 pounds of weight. So this is a really heavy rover as it goes. It's fairly lightweight as cars go. So we also have to get there. So what is the way you get to Mars from the Earth? So we know what we want to take there now and get to the surface, but how do we get it there? So the Earth goes around the sun in 1 Earth year, but Mars takes twice as long. And so when we go around twice for every time Mars goes around once, so every 2 years is when the planets literally align so that we could take off from Earth and then catch up to Mars when we want to get there. And that takes somewhere between 6 to 9 months. And if we were to leave in one of the off years, it takes about a year and 6 months. So we get there almost the same time, but we leave a year sooner. So that's why we wait every 2 years. It's a lot more efficient to get there. And you then need to also, this is what we want to get to the surface, but we want to get there from Earth to Mars. So we have to have power and communications and all of that for between Mars and Earth. And then we also need to get through the atmosphere and onto the surface. So this heat shield and back shell with parachute enter the atmosphere and slow us down, but not enough. So we need this ton of jetpack on our back. It's called the descent stage. So these things here are retro rockets that then slow down the rover. And then from, can't see past the rover, so this surfboard's hanging out here with instruments and radars to see how close you get. Then you lower it down on the cables and release the wheels halfway down. So then you kind of shove it all together, and this lets you know sort of how big it is. It's really, you know, like 4.5 meters across. It's huge. And these are tanks of propellant. And you do a little fit check to make sure your luggage fits where it needs to be. And it all looks like this.
That great things take many people working together to make them happen is one of the fantastic things of human existence.
Not only have we driven the rover, we've moved its arm, put it all through its paces, but it's been in a thermal vacuum chamber and kept very cold. Parts of it have been in a centrifuge. We've done drop tests, pull tests, drive tests, load tests, stress tests. It's just an amazing amount of testing this vehicle has gone through. We've tried every way of operating in the vehicle using the software, literally thousands and thousands of hours of software testing. It's been just an amazing several years, really, of constant testing and development, finding problems, fixing those problems, and going on to the next problem. I think she's ready to go.
This is the LD on channel 1. LC, you have permission to launch. Roger, proceeding with the count.
Minus 10, 9, 8. Confident that she's going to go and she's going to be successful? Absolutely. It's going to go and she'll be good.
Around Mach
So this is a computer simulation.
Accelerating.
Actually, I'm going to turn it on here. Turn it down.
Digital has separated. We're on the ground. Standing by for backshell separation. Right. We're at altitude 1 kilometer descending. Standing by for sky grading. Sky grading started.
Watch the wheels come down.
Fantastic demonstration of what our nation and our agency can do. I could only think of the words of Teddy Roosevelt as I was sitting there. It is far better to dare mighty things even though we might fail, than to stay in the twilight that knows neither victory nor defeat. And the team brought us victory.
The very first picture. So we landed. We were excited. We landed. So we landed. Here's the landing ellipse. We landed right close to the center, just off to the right. So our plan is get to the layers, get over here, go across this plains and get to these really more interesting layers of rock. So the mountains to our south, off to our lower right. So we needed to get there, and the scientists had analyzed every little grid to say what would we want to do in each one of these different areas on our way. And so of course the first thing they said was, but off to the right is really an interesting spot. And why is it so interesting? Because these are geologists. They're interested in different types of rocks that they typically call units. So there was a cratered unit, a bedrock fractured kind of unit, and we landed on this smoother hummocky plains. And you can even see here where the retro rockets scoured the surface as they blew down onto the surface as they set the rover down. So the rover's down in between this, drives over. You can even see from orbit the rover tracks, and this little dot here is the rover itself. So instead of going exactly as we thought, the first thing we did was take a scenic tour off to the right to look at the different rocks. And it's really desolate. So you can see the mountain in front of us kind of starting, and this desolate kind of rocky plains, but you can also see that it changes a bit as we go along. And that's what they're interested in seeing. How do these different rock units, what's different about them? Why do they look so different? Why are we wanting, how much water was here? So one of the things they can do is they can look really close with a camera on the end of the arm called the hand lens imager and get like 1 centimeter from the surface. And when they look at that, they can see that these rocks are actually pretty round and they're cemented together in rocks themselves, but there's several that are loose. And this told them that there's been water here and it's been flowing water such that it's been about, waist deep water that's been flowing, and that's made these rocks round as they abrade in that water. So they've, right off from the very early parts of the mission, we could tell that water had been flowing here, and we weren't sure if it actually flowed or it just was still in this area. When your spacecraft is inside this heat shield and back shell, the power source we have at the back of the rover is called a radioisotopic thermogeneration device. And if you've seen The Martian, that's the thing he uses for heat in his when he's freezing, because Mars' highest temperatures are like just about melting water, right? We're just above freezing, usually on any given day, maybe a bit more in the summer. So we don't have a lot of warmth. You need heat. So that RTG would, in a vacuum, redistribute any of the volatile organic compounds all over the vehicle. So we wanted to be sure that when we were looking for organic molecules, that we didn't bring them with us. So we had to take the sand and send it through that sampling system in sieves to kind of scrub off, like dry wash our hands, to get all of that stuff off of our system before we used it to analyze anything. So that's why you see these divots. And of course we took a selfie. And each of our selfie is with a camera at the end of the arm. And there's 55 images, now 72 when we do this. So we get a little more terrain as we do that. And there's even a video out of the camera taking a picture. So we took a picture of the camera taking a picture, which is actually available out there as well. So that's why you don't see the arm in here, because the arm was over here and the arm was back here, and we can just stitch them together. It's kind of sneaky. So we ended up doing this detour and then coming down towards the rock zones as our path happened. And this white line is actually when we left the landing ellipse. It was kind of like a little, you left your zone of known area, and we're getting into where we could never have been before. So that was exciting. And one of the things we did as we get there, if I go back here, all this black stuff is sand, and it's big dunes of sand, and they wanted to get kind of close to them here. So we get to these sand dunes down here, and they're huge. They're taller than the rover by at least a meter or two. So they're like 10 to 20 feet. I think I said meters before, but it's like 5 to 12 meters, 5 meters or so, like 15 to 20 feet tall. And they're a little dangerous to drive on. You don't want to get stuck in the sand. And these sands, they move like a meter a year. And what we even found is from one day to the next, you could see that they moved. So the wind is blowing in this area, enough. It's not like it's tornadoes, but it's blowing enough to keep the sand moving. And the sand is black, and all the rest of things are sort of rusted, a rust color, because they're oxidation of metals. So we were a little worried about driving in these sand dunes, and particularly in sort of ripples that may be exactly the same height as the rover. And so we took our test vehicle, which we call Scarecrow, because it doesn't have much of the vehicle with it. It's just the drive system. And the reason it's that way is because the gravity on Mars is different than the gravity on Earth. It's less. So we need to have a weighted rover that is weighted so that the pressure on the wheels is the same on Earth as it would be on Mars. So we tried it out and it worked. And then we tried it out on Mars, and we found out that Martian sand and California sand doesn't quite behave the same way, because the sand on Mars has been created by wind erosion, where most of the sand on Earth has been created with water erosion. So the particulates like grab together and behave slightly differently. So we had to adjust our thinking even more when we drove. And about this time, we started looking at the wheels and realized that the wheels are, not only is their sand is a danger, but the wheels are starting to get damage from the surface. And we didn't quite expect that. There's a hole here, and you can see a big flap sticking in. And if this flap comes around, it could cut this cable, because this is 6-wheel drive. Every wheel has a motor in it and 4-wheel steering. So each corner wheel can turn from the top as well. So that was what we were really concerned about. And these wheels are really, really thin. So they're milled out of a single piece of aluminum. They're about 1 millimeter thick, and there's 6 of them, but that's got almost 2,000 pounds sitting down on all 6 of these wheels. So it's kind of like rolling a Coke can in your driveway. You're gonna get dents, dingles, and occasionally you might get a hole. And you may ask, why are they so thin? Well, remember when we were landing, we were on a cable, and those wheels then had to release. That created an impulse. So you don't want a whole lot of weight to pull on that cable. So we needed them to be strong, but yet light as we move forward. So it's always a trade space that you have to do. Should we have thin wheels? Should we have thick wheels? And we also had purposeful holes. So if we got sand inside here, it would work itself out. You know, anything you get inside, you may or may not get out, and you dig yourself deeper, but this would let it out. So how did we get these holes? And then we got this image, which gives you a really big clue. So these rocks, and this one in particular, we thought this one would fall over and get pushed into the sand as we were driving. Before we left Earth, that's what we were thinking. But obviously this thing isn't going anywhere. It's got the whole weight of the rover on it, and the whole wheel is not on the ground. So that was a big clue that perhaps these rocks aren't really giving very much. And sure enough, we got a big hole from driving over that thing, as well as we can see other cracks. So we had a theory that perhaps the sand is more cemented, like those rocks at the beginning of the mission. And so we're thinking it's these cemented in rocks. We call them the pointy rocks, really high tech.
2,
And
1,
we put it in our test bed. And that is how fast the rover goes. That's its only speed. So why is it that we're getting these holes? One, we've got the impaler now. We know that it can do that, but the front ones and the middle ones, we're getting a lot, especially the front ones, we're getting a lot more damage than the rear ones. So why was that? If there's these pointy things and all the wheels drive over them, why is that one worse? Call in physics to the rescue for this one. So if you have a pivot and you're driving, your driving force between all 6 wheels is behind that, you know, the wheel is leading the pivot, you will end up, if you hit this wheelbarrow against a curb, you're just gonna drive that wheel right in and all your load flips over it, right? If you've ever used a wheelbarrow and you hit something, it'll wanna flip right over. And if you're dragging it like a wheel is trailing the pivot, then you end up hitting a bump and you'll just kind of pop over it. So of course, just like any theory, you want to test it. But as we can show you, these front wheels, the pivot's back here. So it's in front of the pivot. So as you're pushing forward, this is just getting shoved into those rocks. And these in the back, the pivot for the middle wheel is here, and the pivot for the back wheel is right here on this here as well. So these two have the pivot behind it. So the rear wheel has a pivot behind. So let's try that test on the rear wheel. So 2,000 pounds can be on a point that would break my skin almost and not go through it. So theory proven. So then we get to an area called Dingo Gap, and we have like 1.5 meters high sand drift here, you know, a dune type of thing that we want to get to this part over here. So should we go around, which I'm calling the high road, or should we go across this scary looking sand dune and take the low road? What do you think? High road, risk the wheels, get some more holes, or low road, get stuck in the sand possibly? Which way should we go, high or low?
High.
High. High road.
High road. Okay, high road versus low road. Well, we chose the low road because we cheated a little in my question. So we can try it and back up. We don't have to do it all in one go. You can gingerly give it a shot, see how it's going. We're tall enough, we can even peek over the other side better. So we took the low road, and if that not worked out, we would have certainly gone to the high road if we'd have been feeling like we slipped in it too much, because we can check for that. And this is what it looks like from the other side. So there were some additional little ripples here that we had to go through. And so that got us through these dunes, and we started up on this, what we call the hematite unit. We renamed Vera Rubin Ridge. Vera Rubin was the one who actually discovered dark energy. And when we were along these lines, along these routes, back here, these are the areas, the clay unit, the Murray Formation, the hematite unit. They wanted to be able to drill holes. They had drilled holes a few times along here, but these are where they're really interested in doing rock sampling. And how do you choose where you're gonna do that? And that's with the laser KimCam. So that KimCam can, each one of these dots is where they had lasered and sampled from afar, you know, laser shot every single one of these, and they can see how much silicate is in it from the KimCam instrument. So they wanted one with less silicate and one with more silicate in it in order to choose where they, so where should I drill? Where should I drill? And get what I'm looking for, so they can use that instrument to tell them. I'm about done here. So, and to doing that, you do a little sampling, you can brush it off to even get deeper. But this is what I wanted to show you. This is a 10 cent piece from, it's the size of a US dime. So this US dime, imagine it on the floor in front of you, and you put your hand up top and you have to hit it with a laser pointer. Not just once, but like 6 or 7 times. That's what the rover has done with that chemical camera into that drill hole. And this is the drill we use at the end of the turret. And it's giving you a sort of a sense of what it looks like when we go down into it. This is how it looks when we're drilling with it, because we've had a problem. We had to actually extend it out. It's not the way we normally use it. And this is how close it has to get to part of the rover to deliver sample. And this is the trap door that we open to put the sample into the chemical, into one of the laboratory instruments. So this is very close. And we got a drill hole, and that drill hole was in May of 2018. And just a month or so later, sandstorm had started up clear around the entire planet, which is eventually what took out the Opportunity rover on the other side, because it's solar powered. Our RTG here kept us from doing that. And so you can see it's a little more pink, and there's sandstorms in the background even that you can see in this image. part of what we've done is we've been looking for methane in the atmosphere, which we knew had been in the atmosphere, but we've been seeing variations that the orbiters can see as well. We're not exactly sure, but it's certainly something happening within the planet that's sending more and less depending on the season, as well as we've discovered the very first organic chemical in a rock. It's called chlorobenzene. And so this chlorobenzene we found at the Cumberland with our analytical instruments. And the question is, how is that biological? It could come from biological things like we have with the dinosaurs and fossils and such, and crude oil and coal. It could be along those lines, or it could be geological. You can add water to olivine and it will break down and make chlorobenzene as well. So it's still not a, hey, we found some idea of life. We have found an organic chemical that could have come from either direction. And we've done this now 21 times. And the only reason I'm showing you sort of the zoom view here is that we've got some that are more gray and certainly some that have a lot more red and rusty kind of look to them. And so the contents have been very different. And they have found from this that this crater has been full of water for not just a little bit. It didn't just fill and drain, it was full for millions of years. It took a long time. And they've then been able to do that by the jarosite, as it turns out. And one of the things they've found also is that the silicates that are in there, some of those silicates are in the form of opal. So the fact that this is not just straight across here, but that it does this arc indicates that it has opal in it. So we actually have a little bit of a gemstone over there on Mars. And that's the only one maybe that we could do. That was exciting to me. So that's what I had to share with you. And I welcome you all of any questions that we have. You can certainly look at us on Facebook and Twitter, and we have all the stuff I showed you is on the web.
I think it's very interesting if you tell them how is the information relayed from the rover to you guys and the other way around.
Okay, I think I even have a picture of that. Hold on. Dust storm.
Oh, there are a lot of slides.
Yeah, so let me get this one here. So yeah, these are all my backups. So the rover's on Mars, and from Earth, we send stuff directly to the high gain antenna, which is about the size of a melon, but it's flat like a ping pong paddle. It's about like a ping pong paddle, and it actually is paddle shaped and it will point. So we go from the Earth through these big antennas to the rover, and that's usually, from the rover's perspective, it's about 10 in the morning. So about 10 in the morning, we send it a program. Drive over there, put your arm down here, do something like that. So we tell it what to do. And then we tune out, and it does it, and nobody sees what happens. It does it all on its own. It's a pre-programmed thing. And somewhere in the afternoon, like Mars Reconnaissance Orbiter tends to come over somewhere in the early afternoon. Odyssey is late afternoon, and these are all over the place because they're not a circular orbit. So these are really elliptical orbit kind of stuff. And we have more orbiters now than just these three. So we send it in the afternoon, and then again in the middle of the night, we can do it as well. So that's what the RTG got us, is we can stay up all night and do work at night, which if you're solar powered, you kind of need the sun to keep your power going. So we send it to one of the orbiters, so we can't send a whole lot of time because they're limited in how much memory they have, and they send it back to Earth for us, and then unpack it and then shoot it over to us. So this is the way we actually communicate with the rover. So one, it's 5 to 20 minutes just to get it from the Earth to Curiosity, depending on where Earth and Mars are in their orbits. So when they're really close together, it's like 4 to 5 minutes. When they're as far apart as possible, it's 20. And so it's not joysticking. We never see what it does. It's do this, how'd it go every day.
Okay, guys, do you have any questions?
I do.
Mm-hmm.
What would you say was your biggest achievement so far?
For MSL, it's really hard. I'd say the organic molecule was a really big deal. And the fact that they could tell that there's been water for millions of years. So I think before we got there, they didn't realize, they knew water had flowed. It's kind of obvious if you look at some of the rock formations, there's alluvial flows and various things. And some of the previous rovers and missions had said, yes, there's definitely been water. And at the pole, there's water ice. So it's clear there's been water here. And the question was, how long? And how long was it sitting here? And so we've been able to push that clock further back. That it used to be not just a little bit, but for a very long period, especially in a crater where it may have pooled for longer than, say, on other parts of the planet.
Thank you.
I have a question.
Salva.
What will you do if the rover gets like damaged? Like, would you have to wait like until it's time to go back there, or?
Well, we end up having issues with it fairly regularly, but we have had some issues. So on Sol 200, it was one of our more serious ones, and that is our rover has really got two big computers in it that run it. So we have independent computers that we can switch between, thank goodness. So on our main computer, RCE, our computer A, as we call it, string A, we were operating, everything was great. And I told you, we send the stuff and we do it, and then the rover goes to sleep and charges its batteries a lot. And so when it wakes up and boots, it then starts everything up again. So you're rebooting your computer all the time. And in doing that, it didn't fully come back up. And it was like, I'll finish this as soon as I'm done with that, right? And it got stuck. And it hadn't gone back to sleep, so it was no longer charging its batteries efficiently. So when we're awake, we can't charge the batteries as much because we're using power as we're doing that. So on that day, we found that we had a memory problem. So we had some memory in our computer go bad, and our response, our automatic response, had a bug that didn't let it respond to it correctly. So we had to intervene and sling up a command to say, switch to the other computer, because usually it would do that automatically, but there was a bug that kept it from doing that. So we forced it over and had to figure that out from afar and then reload the operating system with a new version to miss that, to skip around the bad memory and fix the response to when you have bad memory. So we've been able to do things from afar, and like getting holes in the wheels, we can't go change a tire. So if we get really bad, we're gonna have to figure out in our test bed sort of how to pop off the bad parts, if that ever gets to there. Instead, we're trying to prevent it. And so far, we've been really successful at that. We thought we would be a lot more damaged by now, but all of our interventions of kind of avoiding pointy rocks has helped. And we even put in a flight software to like notice when it's driving and release, let go, stop pushing on one of the wheels. Because it used to be all 6 of them just drive all the time. And so now if it notices one is getting kind of hung up, it'll reduce the force on that one so that it stops damaging the wheels.
What about when you get dust on the rover or particles on the rover?
So we've had like the dust storm, we've noticed there's stuff on top of the rovers and now got more sand on them from the dust storms. A lot of that you really can't do much about. You just have to monitor it. So there's some that have like magnets, and since the dust is all like oxidized metals, they'll stick around the magnets, and that's how you keep it clean. So here's my lens, and I put magnets around it, and the particles will go stick to that instead of my lens. So the field is protecting my lens. So there are events like, so when we were in the Bagnell Dunes area and it was blowing that sand around, it built up sand in some cups, but it also blew off the dust in other areas. So Opportunity would clean off the solar panels this way, but we don't have solar panels, so we don't have quite as dramatic of an activity. But if we have something stuck somewhere, like a piece of a rock stuck somewhere, we may or may not be able to get it out. We can vibrate things. So we do clean off stuff like the end of the arm. We have to if you've ever baked and you had to try and get flour out of a cup and it's not coming out, you end up tapping it, right? We have that inside our sampling system. And we have it in those tubes as well where they receive. So when we're putting sample into a tube, everybody's getting a little tap We have taps on both sides, vibrations, so that we can ensure that the powder, which is very fine, gets out. So we can do that to like help clean off some of the instruments on the end as well of the arm. You vibrate them. You kind of like go like, get it off.
Any other questions, guys?
Does finding water is always related to living organisms?
Is it related to what?
Living organisms.
Well, we think that life, because the life as we know it, is very based on water and on and organic molecules. So you kind of need both in order to do life here on Earth. There's very few life forms on Earth that, very rare, that do not rely on water. So that's one of the reasons we're following water and trying to get water, because that's been the indication of that, and organic molecules are the two things that go hand in hand for life, historically or present.
Thank you.
You're welcome.
So I have a question that is like similar to the last one. That is, so we know that life is dependent on water, but like, could water also be dependent on life?
I don't believe so, because I believe that we found, like, well, we don't know if Europa has life on it, but we found water on other areas, and there's certainly an awful lot of water on comets. Some of the comets are just really big ice balls that are going through the solar system, and those have not necessarily had indications of life on them. Some of them may have organic materials, I don't know that, but we've certainly found places, especially even on Earth, where we have water and no life. We have actually at least one sea in Russia, I can't remember the name of it, that doesn't have very much life below a certain level. Because it's
okay.
tough.
There's a question here on the chat. I'll read it. In Mars, is the atmosphere hostile enough to support a drone? Or if it is, could a drone help scan the territory so the Curiosity knows better its surroundings?
Well, that was very apropos, because the next rover that is our sibling, they used our blueprints. It's called Perseverance, and it launches in July. It actually has a helicopter. So the atmosphere is not very thick, so there's not a whole lot of it. So it's too much to help you land. Like the Apollo astronauts would just use the Earth atmosphere, slow themselves down, and then drop into the ocean. There's not enough atmosphere to do that on Mars. And on the moon, there's no atmosphere, so you could just go and you set yourself down. So there's just enough to screw up everything you want to plan and make it hard. And so they have a helicopter that's going to do exactly what you're talking about. But the drone, the blades have to be like longer than my arm, and they're going to unfold and then swirl around in opposite directions. So they do have a helicopter that they're trying out to see if that's even feasible, because the atmosphere is pretty thin. And so the thing it's carrying has to be very light as well, but also has to get through all the vibrations and temperature swaps and vacuum of getting to Mars. From launch to Mars, there's a pretty harsh environment you have to survive to get there.
Okay, guys, we have time for one more question.
I have a question. If the rover gets damaged, does the NASA have a kind of replace of that piece of part of the rover? And if it's there's a piece, how much time it gets to Mars, or they launch the robot to Earth?
So the only spare parts we have that could be on the rover are things we take with us. So there's no way that I can send a wheel and change it out on Mars. So if my wheel has troubles, That's the way it's going to be. So when Spirit landed, it had one of its wheels wouldn't turn. So if the entire mission, they were dragging one of their wheels around with them, because it took all of this effort, energy, and money to get that rover onto the surface. They're not going to do all of that again just to fix one thing on this rover. Instead, they would build a whole nother one and go somewhere else. And because you basically have to start over if you're sending something else there. So the only things we can change out are things we take with us and anticipate the need for. So on the front of the rover, we actually have spare drill bits. So I can change my drill bit if I dull it or if I break it or if it gets stuck. We can release the drill bit and put another one in, but that's it. That's the only thing I can change out. Everything else we either have to live with or figure out how to deal with. So your old car, if it's, you know, the vent doesn't work, the heater doesn't work, you're just going to be cold and you have to figure out how to deal with it.
I have one more question. I'm sorry. I just wanted to know, are you guys planning on bringing it back? And if so, when? And nope. Not bringing it back, not ever?
Nope. All those dots you saw on that first map, they're still there. The one from the 70s Viking, it's still there, which is why in the Martian, they could go dig up one. That's what they did. They went and found an old one and dug it up because they're all still on the surface. I didn't bring a launch vehicle to send it back, and we're not planning to go get it. Even
So if you're not gonna get it back, what are you gonna do with the samples that you're taking?
Those samples that we're taking go into we brought the laboratory with us. So we put them into our lab that we brought with us. So we basically brought part of your chemistry lab with you, and acting like a geologist, we brought the geologist and the laboratory. So we do it all on site. Versus the next mission is planning to drill samples that come back and put them in tubes and leave them for another mission to come get them. So they are still not sending them back. They will leave them on the surface, and that sample may not come back until 2030 to 2040, somewhere in there. 2030 to 35 is when those samples might actually end up back on Earth. It'll take that long. And 3 different spacecraft to do it. You need an orbiter, a launch vehicle, a way to bring it back. It's complicated.
Okay. Thank you very much, Dr. Allbaugh, and thank you very much, guys, for joining. I hope you learned a lot. If you have more questions, send them to me via email, and I'm going to forward them to Dr. Allbaugh, and she will see when she can answer them. Or she
Yes.
Okay.
Thank you, everyone.
You guys have another class in 3 minutes.
Yeah, I was like, you guys are cutting over close, aren't you?
Bye.